Yes, please put the heading as a infinite Fourier sine and cosine transform. Infinite Fourier sine and cosine transform. Infinite Fourier sine and cosine transform. From the these definitions are derived from the definition of Fourier transform. Definition of Fourier transform. From the definition of Fourier transform, if f of x is an even function, f of x is an even function, then you can get this kind of relation. This kind of relation, and that you will get here. You will get. Suppose f of x is an even function in the Fourier transform definition, f of x, that will be 1 by root of 2 pi integral minus infinity f of x e power minus isx dx. This is Fourier transform definition. Suppose f of x is an even function. F of x is even function. Then what you can get here, 1 by root of 2 pi. F of x is even. Then you can split it as cos sx minus I sin sx, minus I sin sx. This is even and this is odd. You can get odd, or you can get as root of 2 pi pi. 2 into 0 to infinity. Therefore, root of 2 pi pi f of x cos sx dx. Cos sx. This result is a function of s here, and this transform is called as a Fourier cosine transform because it comes as a only cosine involves here. Therefore, this is called a Fourier cosine transform here, and it will be termed as a FCF f of x. FCF f of x. FCF f of x. This result is very obvious. This FCF s is also even. This FCF s is also even because if s is minus s, cos or minus theta, cos theta here. Therefore, that this functions will not be altered here. This will also even function here. Even function. Correspondingly, FC of s is also even. Is also even. Even f of s is also even. Then by inverse Fourier transform, transform, we get another one f of x as a that fs of s also even function. Therefore, looking at this root of 2 pi by integral 0 to infinity f of s cos sx ds only you can get. This is under cosine transform. Therefore, this FCF s you put that here. So this is called inverse Fourier cosine transform. This definition is called inverse Fourier cosine transform. Inverse Fourier cosine transform, and this is called Fourier cosine transform. This is called Fourier cosine transform definition. Fourier cosine transform definition. This is Fourier cosine transform. This is inverse Fourier cosine transform. Came from the Fourier transform definition. Similarly, f of x is odd. Odd means this is odd function, this is odd and odd even. Therefore, you can get sign relation. That sign relation you can get. But odd and odd even here. This I, because we are going to treat it as a transform here. We are going to treat it as a transform. Therefore, we remove that I. Remove that I. We are going to consider only that integral part only. F of x cos sx. This is FCF. That will be termed as f of s, and this will be fs of s cos sx. So in that manner we can. Therefore, definition. These definitions are purely considered by taking fs of s is an odd function, fs of s is an odd function, and f of x is an odd function and even function. That type of idea we can get. Right there, from the definition of Fourier transform, if f of x is an even function, if f of x is an even function, if f of x is an even function, we have the definition of infinite Fourier cosine transform, infinite FCT, infinite Fourier cosine transform, infinite Fourier cosine transform. Within bracket IFCT or simply FCT. Sometimes IFCT or simply FCT also possible, or FCT, and is defined by FCI f of x, because Fourier cosine transform, therefore we use the notation C. FCI f of x is equal to root of 2 pi pi. Instead of 1 by root of 2 pi, we can use root of 2 pi pi because of 2 into 0 to infinity, that idea. But that 2 in the root to get cancel, you can get root of 2 pi pi. Root of 2 pi pi, integral 0 to infinity f of x cos sx dx, f of x cos sx dx. That is equal to, the result will be a function of s, where it is under Fourier cosine transform, therefore use the notation FC of s. Instead of f of s, use the notation as FC of s, because it is under from Fourier cosine transform, therefore you can use FC of s. F of x cos s x, everything is x. Similarly like that, and its inverse IFCT is given by, inverse FCT or inverse IFCT, any manner can write. Inverse IFCT is given by Fourier cosine transform is given by f of x. With the help of inverse, you can write f of x, is equal to root of 2 pi pi integral 0 to infinity integral 0 to infinity FC of x, complete cos is equal to, okay, right. Similarly, when f of x is an odd function, by Fourier transform definition, we have the definition of infinite Fourier sine transform. We have the definition of infinite Fourier sine transform, and termed as IFST or simply FST, Fourier sine transform or infinite Fourier sine transform. IFST or FST, and is defined by Fs of f of x, because of Fourier sine transform, use the notation as Fs of f of x equal to root of 2 pi pi integral 0 to infinity f of x sin sx dx, everything is x. Result will be a Fs of s, function of s, but under sine transform, therefore you can use s. S may be small or capital letter, no problem. Fs of s, and its inverse IFST, inverse infinite Fourier sine transform or infinite Fourier sine transform, inverse Fourier sine transform, is given by f of x equal to root of 2 pi pi 0 to infinity Fs of s sin sx ds. Yes. Fs of s sin sx ds. Or here can use 0 to infinity. Yes, these were the definition of Fourier sine and cosine transform. We'll see some properties based on this Fourier sine and cosine transforms. Fourier sine transform and cosine transform are linear. FST and FCT are linear. FST and FCT are linear. That is FC of A f of x plus B g of x. FC of A f of x plus B g of x is equal to A into FC f of x plus B into FC of g of x. Similarly, Fs of A into f of x plus B g of x, A f of x plus B g of x is equal to A into Fs of f of x plus B into Fs of g of x. Proof it is obvious from the definition because it is integral operator. That's obvious. It is obvious from the definition. Second one, modulation theorem. Modulation theorem. MOD. Modulation theorem. Modulation theorem. First one, Fourier sine transform. Fs of f of x cos ax. With f of x, cosine function is multiplied. F of x cos ax. And that is equal to 1 by 2 of Fs plus a. Again involves sine transform. Fs plus a plus Fs of s minus a. Fs of s minus a. Again, both involve sine transform. When f of x is multiplied with the cosine function, result will be a sine transform. Number 2, when f of x is multiplied with the sine ax, f of x is multiplied with the sine ax, then it's Fourier cosine transform. Fc of f of x sine ax. Fc of f of x sine ax. That is equal to 1 by 2 of, it is also the result of Fs of a plus s, Fourier sine transform. Fs of a plus s plus Fs of a minus s.
Sir, for cosine transform,
plus Fs of a minus s. Proof. First one, solution 1, Fs of f of x cos ax. When f of x is multiplied with the cos ax, then it's Fourier sine transform. Sine transform means sin sx instead of f of x. F of x we have to write f of x cos ax and the sin sx dx. That's equal to root of 2 pi integral 0 to infinity f of x cos ax instead of f of x cos ax, sin transform sin sx dx. Then club this cos ax sin ax separately, f of x separately. The next integral. Now this cos ax sin ax sx like a sin a cos b form, sin a cos b form, sin sx 1 by 2 of, therefore can be written as sin a cos b can be written as 1 by 2 of sin a plus b sin a minus b. So that is equal to root of 2 pi integral 0 to infinity f of x 1 by 2 of sin a cos b sin sx plus sin a plus b sin a plus b sin sx plus ax plus sin a minus b sx minus ax. Then split the integral for this addition of two terms. This addition, not this addition, this addition. This addition. Then 1 by 2 also take it outside here, 1 by 2 root of 2 pi f of x sin of s plus a of x dx. We take x commonly, s plus a of x dx plus root of 2 pi sin of s minus a of f of x into sin of s minus a of x dx. Very simple proof only. It is like a sine transform definition, both are sine transform, but instead of s plus a, here instead of s minus a. Substitute them. This space over.
Yes.
Then 1 by 2 of fs of s plus a, fs of s minus a. Fs of f of x cos x equal 1 by 2 of instead of s plus a, instead of s minus a, sine transform definition. Sine transform definition. Instead of s plus a, instead of s minus a. Similarly, second subdivision, fc of f of x sin x, fc of f of x sin x, which is cosine transform, root of 2 pi into 0 to infinity instead of f of x sin ax, cosine transform cos sx dx, cos sx. मतलब this sin ax cos sx. Again, it is like a sin a cos b form. Therefore, sin a plus b, 1 by 2 of sin a plus b. A plus b means x is common, a plus s of x plus sin a minus b, a minus s. Yes, 1 by 2 root of 2 pi f of x sin of a plus sx dx plus root of 2 pi f of x sin of a minus sx dx. That's all. Instead of the sine transform, instead of s a plus s, instead of s a minus s, a plus s a minus s. This is for your exercise third and fourth. I can use all of you just note down. There are two subdivisions here. You can try in the leisure time. Also, you can use the formula of cos a cos b, 1 by 2 of cos a plus b cos a minus b. Sin a sin b, 1 by 2 of cos a minus b minus cos of a plus b. All of you just note down third and fourth one. For your exercise. Tapida.
Yes, sir.
Okay. Right. Third property. Right. If fc of f of x, Fourier cosine transform f of x equal to fc of s, Fourier cosine transform f of x equal to fc of s, and Fourier sine transform f of x equal to fs of s, Fourier sine transform f of x equal to fs of s, then fc of f of ax, fc of f of ax equal to 1 by a fc of s by a, 1 by a fc of s by a, and fs of f of ax, Fourier sine transform f of ax equal to 1 by a fs of s by a, fs of s by a. This is change of scale property. Already you studied in the Fourier transform, the same idea. Now consider Fourier cosine transform definition. By definition, Fourier cosine transform f of x equal to root of 2 pi 0 to infinity integral 0 to infinity f of x cos SST is Fourier cosine transform f of x cos SST is. That is equal to FC of S. Fourier cosine transform. Now we consider FCI f of Ax. Instead of f of x here, f of Ax. Root of 2 pi 0 to infinity f of Ax cos SXT. F of Ax cos SXT. And put Ax equal to y to get the result here. Put Ax equal to y, x equal to y by a, dx is equal to dy by a, and no change in the limits. When x is 0, y is 0, when x is infinity, y is also no change in the limits. Correct? And substitute here everything here f of y, this is f of y cos s, x is as a s by a, x is as a y by a, here dx is as a dy by a, no change in the limit. Therefore root of 2 pi integral 0 to infinity f of y cos s of y by a dy by a. Club this a with s here, this s. Then we take 1 by a outside of the integration, 1 by a. Root of 2 pi 0 to infinity f of y cos s by a y dy. Cos s by a y dy. And that's equal to fc of f of x. fc of f of x.
Sir?
It is like a Fourier cosine transform definition.
Sir,
Uh,
someone calling.
Sir?
Mia.
Ashwath is calling. Sir.
Ashwath is calling Mia, or you are
Something is asking. Sir.
Sir, I have a doubt.
asking? Tell that.
Sir, FC of
Hello?
f of Ax, no, sir.
Your voice is not clear. FC of?
FC of f of Ax, no, sir.
FC f of x.
But in PPT, FC of f of x, it is there, I think. Yes, sir.
Oh, sorry. Okay. FC of f of ax. It's not f of x, f of ax. Fourier transform, cosine transform definition 0 to infinity f of x cos sx dx form. But instead of s here, s by a. Or you change fc of s by a. Fourier cosine transform, therefore fc of s by definition. Similarly, you can get the answer for sine transform also. The same thing for sine transform. Can you give the answer? Can you try? Your answer will be, you put ax equal to y, the same idea.
One by a.
1 by a.
Fs of s by a.
Very good. Fs of s by a. Very good. The same manner you have the another property. Fs of x f of x. Fs of x f of x, Fourier sine transform of x into f of x when f of x is multiplied by x. Fs of x f of x is equal to minus d by ds of fc of s. It comes as a Fourier cosine transform. Fourier cosine transform minus d by ds of fc of s. And number 2, similarly, fc of x f of x. Fc of x f of x equal to d by ds of fs of s. D by ds of fs of s. Where you know already fc of s is Fourier cosine transform f of x. Fs of s is Fourier sine transform of f of x. Fourier sine transform of f of x. Right. As use the Fourier cosine transform first here. By definition of Fourier, in order to prove this one here, you take right to left here. You prove this property by right to left because x into f of x, that type of property, always proved with the help of right to left form here. Therefore, by definition of Fourier cosine transform, we have Fourier cosine transform of f of x. Fourier cosine transform of f of x equal to root of 2 pi pi 0 to infinity f of x cos sx dx. F of x cos sx dx equal to fc of s. You take right to left here, that is fc of s equal to root of 2 pi pi 0 to infinity f of x cos sx dx. Cos sx dx. Right. Now differentiate both sides with respect to s. Differentiate both sides with respect to s. This equation with respect to s. Then what you can get here, d by ds of fc of s. D by ds of fc of s. That differentiation right side moves inside the integration as a partial derivative. Moves inside the integration as a partial derivative, 0 to infinity dou by dou s of f of x cos sx dx. Dou by dou s of f of x cos sx. Now integration with respect, differentiation with respect to s partially. There's no s here, but here s is here. About f of x as it is cos sx, definition is minus sin sx into x dx. Okay, minus sin sx dx. So you can club this x here, and I will take minus outside here. I will take minus multiply by minus here, or minus outside. So minus d by ds of fc of s, minus d by ds of fc of s is equal to this x into f of x here, x into f of x sin sx dx. Now it is like a Fourier sine transform definition, sin sx 0 to infinity root of 2 pi pi. But instead of f of x here, x into f of x is present. But sine transform definition. So this is Fourier sine transform x f of x. Fourier sine transform x f of x, right side. But left side is d by ds of minus d by ds of fc of x, which comes from the Fourier cosine transform definition. Can you try similarly from Fourier sine transform definition and differentiate with respect to s? Take Fourier sine transform definition and differentiate with respect to s. Similarly, you take Fourier sine transform, this like this one, and differentiate with respect to s. Can you give the answer? Differentiate with respect to s. The same manner, you take Fourier sine transform and differentiate with respect to s.
Complete.
Same result, huh? FC of XF of X. Okay. Move on to another property, fifth one. Fifth one. First one is interval 0 to infinity. This 0 to infinity f of x g of x dx is equal to interval 0 to infinity fc of s gc of s ds. fc of s gc of s ds under cosine transform. F of x cosine transform is fc of s. G of x cosine transform is gc of s. That both intervals are same. Similarly, suppose you have f of x sine transform is fs of s, g of x sine transform is gs of s, then their product integrations are equal. Number 2 is interval 0 to infinity f of x g of x dx. That's equal to interval 0 to infinity fs of s gs of s ds. fs of s gs of s. All the three intervals are same. This one equal to this one equal to this one. All the three integral values are same. Okay. If we know sine and cosine transform definitions, sine and cosine transform definition. Just use the definition. That's all. First, you consider the either left side or right side. Any manner can prove that, no problem. If you use left side, you have to use inverse Fourier sine. If you use right side, you take Fourier sine or cosine. Consider right side here, interval 0 to infinity, first one, fc of s, gc of s ds. Now this gc of s is Fourier cosine transform of g of x. This is equal to Fourier cosine transform of g of x ds. Fourier cosine transform of g of x ds. fc of s as it is, gc of s is Fourier cosine transform of g of x ds. This is what is Fourier cosine transform definition of g of x. Then I root out 2 pi pi into 0 to infinity g of x cosine transform definition cos s x dx. Interval 0 to infinity, this is as it is, this is fc of s as it is here, ds is as it is. Now I will club all the two integrations here, root of 2 pi pi outside, 0 to infinity, it is also 0 to infinity, fc of s g of x cos sx dx ds, cos sx dx ds. So write all the, you club all the two integral and the functions here. G of x cos sx dx ds. Now this integral is with respect to x first, with respect to s next here. I will change the order of integration. I will change the order of integration. Then ds s first and x next. When you consider s first and then x next, s first x next here. Here s is percent, here s is percent, s is percent. And also I will club this root of 2 pi pi for that s integral. Now I will club root of 2 pi pi 0 to infinity, 0 to infinity, s relations first here. fc of s, s here, fc of s, cos sx. This is x and this is x here, we keep it separately. fc of s cos sx ds and the g of x dx separately. G of x dx separately. The change of order of integration. The change of order. I will club root of 2 pi pi here, further here. Root of 2 pi pi 0 to infinity fc of s cos sx is. Now it is like a inverse Fourier cosine transform. Inverse Fourier c is here. So inverse Fourier cosine transform of f of x. Cos sx, f of x. So this result is nothing but f of x. F of x by inverse Fourier cosine transform. So this whole integral this whole integral represent f of x because it is the inverse Fourier cosine transform of f of x. Inverse Fourier cosine transform of f of x, therefore f of x. Now only one integral, only 0 to infinity. This is whole thing is f of x. Already a g of x dx is possible. No, g of x. Now this will be your idea. Just use for both inverse and ordinary transform. You can get the result. Left side is integral 0 to infinity fc of s gc of s ds. Left side is integral 0 to infinity fc of s gc of s ds. The same way, if you consider left side, right side again, integral 0 to infinity fs of s gs of s ds. Fs of s gs of s ds. You can get integral 0 to infinity f of s g of x dx. The same procedure. Right, gs of s, it is Fourier sine transform of g of x, and then change the order of integration, you can get this one. And this result over. This property over.
Yes, sir.
Okay. Then move on to a very important property, Parseval's identity. Parseval's identity. The previous property also very important. With the help of that only you can prove Parseval's identity. And this property also important for some problems. Product of f of x, g of x, two functions equal to product of their transforms, either Fourier cosine or sine. Product of two functions integral equal to product of their transforms integral, either maybe cosine or sine transform. Now with the help of that we have the property Parseval's identity. Parseval's identity. Integral 0 to infinity mod f of x square dx. Integral 0 to infinity mod f of x square dx equal to integral 0 to infinity mod fc of s square ds. This is Fourier cosine transform of this f of x. Fourier sine transform of 0 to infinity mod fs of s square ds. Okay. Where fc of s is equal to Fourier cosine transform of f of x and fs of s is equal to Fourier sine transform of f of x. Now, by the previous property, proof is by the previous property, by Fourier cosine transform. For Fourier cosine transform, we have integral 0 to infinity f of x g of x dx. Integral 0 to infinity f of x g of x dx is equal to integral 0 to infinity fc of s gc of s ds. G of s gc of s ds. fc of s gc of s ds. In order to prove Parseval's identity, what you have to take here, you take g of x as a conjugate of f of x. G of x is a conjugate of f of x. You have to prove that gc of s is also conjugate of fc of s. And gc of x is a conjugate of fc of s. fc of s. Okay, right. Let us take g of x, the conjugate of f of x. G of x is equal to f of x bar. Let us take g of x as a f of x bar. You have to prove that gc of s is equal to fc of s whole bar. Let us take g of x is equal to f of x whole bar. F of x whole bar. We are taking bar in this integral. I will consider fc of s first. fc of s. Take fc of s, then that will be somewhat understandable one. Then fc of s is equal to root of 2 pi pi cosine transform of f of x. It will be cosine transform of f of x. We have to identify what is fc of s whole bar. It is real Therefore, no use of bar. This is we don't know about your take bar. This is real function. Conjugate is as it is only. This only we don't know. Therefore, you take conjugate. FCFS. F of x whole bar now taken as a g of x. G of f of x whole bar now taken as a g of x here. Now what is this definition? Root of 2 pi by 0 to infinity g of x cosine transform. This is cosine transform of g of x. Cosine transform g of x is equal to gc of s. Yes. Now we have taken that fc of s as equal to gc of s. Implies fc of s whole bar equal to gc of s. You have taken g of x is equal to f of x whole bar, then you prove that fc of s whole bar equal to gc of s. F of s whole bar equal to gc of s. fc of s whole bar equal to gc. gc of s can be written as fc of s whole bar. Suppose substitute these results here. That is, if g of x is equal to f of x whole bar, g of x is equal to f of x whole bar, then gc of x is equal to fc of s whole bar. gc of x is equal to fc of s whole bar. I must substitute this in equation number 1. Substitute this in equation number 1. And this is equation number 1. Substitute. It will be changed as a f of x whole bar. This will be changed as a fc of s whole bar. F of x whole bar means f of x whole bar is f mod f of x square. Or f of x whole bar. This will be fc of s whole bar. For here mod f of x square, mod fc of x square ds. Wow. Similarly, you can prove this result. Prove the same result for Fourier sine transform. You can prove under Fourier sine transform. Interval 0 to infinity mod f of x square dx is equal to mod fs of s whole square ds. Interval 0 to infinity mod f of x square dx equal to mod fs of s square ds. The same thing you can prove, the same type of idea. Okay. In order to prove this result, what you have to take here, 0 to infinity f of x g of x dx of sine transform is equal to fs of s gs of s ds. You take g of x as a conjugate, you have to prove that this is a conjugate of this one. Right? That's all. With the help of the previous property proof only, we can identify. Take g of x conjugate, gc of s is a conjugate. You have to prove that way. For that, you take conjugate of c of s. Obviously, you can get that. These properties are very important. We can apply these properties in the coming problems here. You can see problems in tomorrow class here. Tomorrow class we will see problems here. Is there any doubt in the so far properties here? You can ask. Oh. Okay. Is there any doubt or any slides I have to show once again here?